My name is Kevin, a second-year undergraduate studying mathematics and computer science. I'm studying at Wadham College, and this is my video that I made for this Computer Science Open Day. I hope you enjoy it, and if you want to see more videos like this, be sure to check out my YouTube channel, Tautime, spelled Tautime, where I do mathematics and computer science that I find relaxing, and hopefully you could too. Welcome. I'm glad you could join me today for my exploration of something called lazy evaluation, a topic in computer science from functional programming. Lazy evaluation is a simple but powerful idea that lets us reason with really big things. And first, we're going to talk about what lazy evaluation is using the programming language Haskell. And then we're going to look at an interesting case study, which is about modeling the Library of Babel, a fictional library that contains every single possible written work. So this library is unimaginably huge. Lazy evaluation, if I were to put it in a nutshell, would be a way of problem solving or a way of doing computations where we only do what is necessary when it is necessary. And we do that by storing the recipe of how to do our computation rather than the result of all of our computation. And this is as opposed to what's called eager evaluation, which is calculating everything and reducing it, evaluating it as soon as we can. For example, if we had a list of values of complicated expressions, such as the 100th powers, the first 100th powers, written in a list like so in Haskell. If you were to evaluate this list completely, and what that means is reduce all to the power of 100 expressions into flat numbers, to really long numbers, then it'll take us quite a while, because even with a pretty fast algorithm, raising to the 100th power is going to take something like 7 steps. And if we're going to do that for each of the 100 values in this list, that's going to get us to something like 700 steps needed. But depending on what we're doing, we don't need to evaluate everything. For example, if we just wanted to know the 10th value in this list, that is 10 to the 100, we don't care about what 9 to the 100 is or what 100 to the 100 is. So with lazy evaluation, we leave the rest of the values alone, go to the 10th place in the list and go, okay, we just need to calculate 10 to the 100. And after doing that, we return the result. So in this use case, lazy evaluation helps us reduce our work because we don't do anything unnecessary. And I'm going to repeat that slogan: do what is necessary when it is necessary. Now, the second slogan I have for lazy evaluation is it lets us reason with infinity in a finite world. This is saying that with lazy evaluation, we could now hold infinite or extremely large data structures in our program, even though it may seem like these data structures are unimaginably huge or that you cannot possibly fit them into your computer's memory. A simple example of this is the list of all natural numbers, which in Haskell is written brackets, square brackets, and then 0, ... And it'll go 0, 1, 2, 3, and so on. Another example would be all possible chess games. So to construct something like this, we would start with some data structure representing our chessboard at the beginning of a game. And then we could write some function that, given a chessboard, gives us all the possible next moves from this chessboard. And so to create a data structure of all the possible chess games, we would be applying this function over and over again in a specific way, so that first we start with our one initial chessboard, and then we would branch into all of the chess games that come after one move, and then branch into all the ones that come after 2 moves branch into all the ones that come after 3 moves, and so on. And this one, if we're not careful, could be an infinite data structure. Because unless we put in the special rule in chess where if the same board position has appeared 3 times, then it's a draw, then what happens is that we could have these branches of this chess game tree that looks like the same few board positions repeating because the 2 players are just moving the same pieces back and forth without doing anything meaningful. But then with this infinite data structure, we could easily program and reason about questions like these ones. Questions like, does there exist a 4-move checkmate from the start of the game? If you were to ask this question, the data structure will not evaluate this entire huge tree. It would only evaluate the first 4 moves and search within that. And notice that we don't need to make a separate data structure for just the first 4 moves of a chess game. We could just use this infinite data structure, and lazy evaluation stops us from computing more than what's necessary. The third slogan that I have, the third and final slogan for lazy evaluation, is that we can observe a black hole without entering it. Now, what do I mean by this? So, a black hole, as you might know, is an extremely dense object in space. And if we move past what's called its event horizon, if we move close enough to it, then nothing in the universe can escape, not even light, because the gravitational force is so strong within that event horizon. Yet we could still know something about the black hole. We could observe its mass, we could observe the little bits of radiation that comes out of it, we could observe how wide its event horizon is, this kind of thing. Now, in a program, by black hole I mean an undefined computation, or a computation that either throws an error because we do something like divide by 0, or a computation that goes on forever because it's stuck in an infinite loop, or something like that. So, lazy evaluation lets us actually observe and work with these undefined values. For example, consider the expression, if not null x's, then head x's, else 0. So in this case, x's is a list, and null x's is a function that returns true if x's is empty, and false otherwise, and not negates the true or false. So not true is false, and not false is true. And head x's returns the first thing in the list if it exists and throws an error otherwise. So this whole conditional is saying, evaluates to the first thing in the list if it exists, otherwise 0. Now, this expression does work because of lazy evaluation, even though head x's would not be defined if null x's were true. This is because unless the condition passes, unless not null x's is true, head x's would never be evaluated. And if this condition is true, we could guarantee by the definition of head x's that head x's will not crash our program. So this feature is so useful, it's so expressive that actually most programming languages have this built in, where the conditionals are lazy. We don't evaluate what's in the then or the else clause until we need it, even though most programming languages are not so lazy. On to our case study, the Library of Babel. The Library of Babel is the creation of Argentinian author Jorge Borges in early 20th century. And according to libraryofbabel.info, which I think must be the website of his biggest fan, since this website recreates the Library of Babel online. The Library of Babel is a place for scholars to do research, for artists and writers to seek inspiration, for anyone with curiosity or a sense of humor to reflect on the weirdness of existence. In short, it's just like any other library. This library contains every possible piece of English text or text written in the Latin alphabet, a certain length. The fascinating thing, or a fascinating thing about this idea, is that this kind of library would contain every book that has ever been written, every book that ever could be written, including every play, every song, every scientific paper. So that would include every computer program or every mathematical theory, every piece of scripture, and so on. The Library of Babel.info website manages to recreate this kind of huge data structure online, and they do it with some number theory and cryptography that I don't really understand. But with lazy evaluation, we could achieve something similar. We could create our own kind of Library of Babel. Perhaps the simplest kind of Library of Babel imaginable, which is given a list of characters, how can we create the list of all strings using these characters of a certain length? Maybe all strings of length 10 English letters, or something like this. Or all 100-digit numbers, which is using the character set 0 through 9, with 100 being the length. To an example of what we want. Let's say that our character set were the two characters A and B, and that we wanted all strings of length 2. Then our list would have 4 characters in it. It would have, or 4 strings in it. It would have AA, AB, BB, and BA as the 4 strings. And this list, you might be able to see that it's going to grow exponentially as we increase the length. It is going to get huge really fast. And that is where lazy evaluation could help us. Let's talk about how we could generalize this example to generating strings of larger and larger length. And we're going to do it step by step. That is, we're going to try to use all the strings of length n to figure out what the strings of length n plus 1 are going to be. And the key observation is this. Every string of length n plus 1 has a prefix of length n, so it is composed of first a string of length n, and then a string of length 1. Well, strings of length 1 are just all the characters put into a string. So this means that if we take all possible strings of length n and on the end put all possible characters, then we would create all possible strings of length n plus 1. And so if we were to do this idea recursively, by recursively I mean we're going to keep on repeating this observation over and over until we can't. This is what happens. Construct all strings of length n. First, we're going to construct all strings of length n minus 1. And then we're going to put all possible characters to their n. But to construct all strings of n minus 1, we must construct all strings of length n minus 2. And so we must construct all strings of length n minus 3, and so on. This leaves us with a problem, which is that our program doesn't know when to stop. If we continue this process, eventually it'll ask for, what are all possible strings of length 0? What are all possible strings of length -1, length -2, length -3? And you can see how it's not going to terminate. So we're going to need what's called a base case. A base case is just a special case of our idea for when we want to stop. And the place we want to stop here is either length 0 or length 1. I'm going to say length 0 because length 0 is nice. Length 0. What are all the possible strings of length 0? Well, if we were to make a string of length 0, we would have no choices about what characters to put. The only string we could make is the empty string. Or in other words, there is a unique string of length 0, and it's the empty string. So with length 0, we're going to return just a list with the empty string inside of it. Let's write this in code. We're going to call the list of all strings of length n every cars n. So this is a function called every, which takes in two arguments. Cars, our character set in a list, and n, which is the length that we want. Now we're going to write this in Haskell, but it's going to look pretty much exactly like how I explained it earlier, where we would take a list of all characters of a smaller length and then put individual characters on the end. So this is what it's going to look like. It's going to look like prefix, a string of length n, prefix, concatenated with a string with a single character in it. And the double plus is concatenation. Or for those familiar with it, you may know it as cat. We're going to write a bar and specify what prefix and car are going to mean. So I'm going to say that prefix is going to be every possible string of length n minus 1. In other words, every cars n minus 1. While car is going to be every possible character. So car is going to come from cars. And you can see that in this way, we're going to have a list of every single possible string of length n with an extra character put at the end, where the extra character is every possible character. And now we just have to write the base case in code. Every car 0 is just going to be the list with the empty string inside of it. Having every cars n is nice and all. We have, in a sense, our own Library of Babel, and we could do things like search for text within it. But there are a few unsatisfying things, like how the order of this list is way too predictable. We know exactly where each word is going to show up. And there's no mystery, not like the real Library of Babel, or a real library, where we don't really know what we're going to find on the next shelf, if it's going to be an old book, a new book, or something completely unexpected. A possible solution to this is to add some randomness, add some random spice into how we define every cars n. And this random order could spice things up so that every time we run it, we're going to get an all-new Library of Babel that's unpredictable, unless we know the random seed. Finally, I want to talk about the geometry or shape of the library. So in Borges' original short story, he does have a description of what the library should look like. Let it suffice for the moment that I repeat the classic dictum. The library is a sphere whose exact center is any hexagon, and whose circumference is unattainable. And there are also many more pages of descriptions, but I want to focus on this. Every hexagon in the library is a center, and the library has no circumference. My proposal for what shape the library could take then is a torus, or a donut. So the reason I choose this is because it's quite easy to code. One way of thinking about a torus is to take a rectangle, glue the left and right edges together so they become the same, and then glue the top and bottom edges together so they become the same. In effect, you get something like Pac-Man, where when you keep traveling right, eventually you'll come back from the left of the world. Or if you keep traveling upwards, eventually you'll come back up from the bottom of the world. A torus is special because it is finite, the area is finite, but has no bound, which means that every point on a torus could be thought of as a center, fitting Borges' criterion. And the way that I'm going to make a torus is first start with every cars n. This is a bit like an origami recipe, which I'm going to draw out as a line where every point is a string, a possible string of length n. I'm going to restructure it to become a rectangular grid. And then I'm going to make this grid into a torus by sticking the top and bottom edges together and the left and right edges together. And I did write a program for this, but I didn't have a nice visualization for it. A few ways we could generalize this is to actually make the library three-dimensional by modeling the height of the library and then using generalizations of a torus, such as a 3 torus, which is achieved by sticking opposite faces of a cube together. Other things we could do is to actually make the library have a hexagonal structure, like in the short story, or even add some randomization, like we discussed earlier, so that the library appears mysterious and vast and unexpected, and all of these things. This is where my exploration is at so far. I hope you found something nice or interesting that you could take away with you. If you like this, check out the rest of my YouTube channel, where I do math and computer science in a relaxing fashion.